Good day, everyone, and welcome to another problem solving session with Special Maths Academy. And we'll be looking at the 48th problem from the Nigerian Mathematics Olympiad, first round, senior category, 2020. So let's go straight to the problem. So which of the following holds for all positive integers A, B, C, and D? And we're giving curved brackets to denote GCD, that's greatest common divisor, and square brackets to denote least common multiple. So before I move on, I will just state some properties of GCDs and LCM. So from the fact greatest, so I won't prove some of these things. I'll leave them to you to prove. And I would like to see you guys, comment your ideas in the comment section. So from the keyword greatest, so we have that if we have a divisor of A, so if R divides A and R divides B, then R divides the greatest common divisor of A and B. Okay, so R divides D. Okay, and you can try and prove this. And then we have II. Okay, so the LCM. So if we have R divides A and S divides A, so that is A is a multiple of both R and S. So we're talking of the least, the minimum. So the LCM of R and S, so the least common multiple of R and S divides A, which is also a multiple of R and S. Okay. And so we'll just take note of this. So you can try proving this during your free time. You can always share your comments in the comment section. Okay, and so moving on, before I move on, I'm going to drop a link for you guys to read more about GCDs and LCM. So link for GCD and LCM in description. Okay. So before I move on, in mathematics, a statement is either true or false. And if a statement is false, one counter example is good enough. So if a statement is false, then to show it, one counter example is sufficient. Okay, so I'll just start quickly by disproving A and C. Okay, so let's look for a counter example. So for A, if we put A, B, C equals 1, 2, 3. So for A, we put A equals 1, B equals 2, and C equals 3. What do we have? We have that the LCM of A of 1 and 2 times 3, so that's the LCM of 1 and 6. Is equal to the GCD of the LCM of 1 and 2, which is 2, and the LCM of 1 and 3, so A and C, which is 3. And so this is equal to 1. And we have a contradiction because so having 6 is equal to 1. And so we see that option A is false. Okay, and let's go to option C, which is the other one I said I'm going to disprove. So we can, for option C, I mean, you can find your own counter examples, but I just found this and I'm going to use them. So if you put A equals 4, B equals 2, and C equals 6. Okay, so we have the LCM of the GCD of A and B, which is 4 and 2. The GCD of 4 and 2 is 2. The GCD of 4 and 6 is 2. So the LCM of 2 is 2. The LCM of 2 and 2 is 2 rather. So I'm looking at the GCD of 4 and 2 times 6, which is 12. The GCD of 4 and 12 is 4. So I have 4 equals 12, and I have a contradiction. So we mark bad for option C. Okay, so it means A and C can be the answers to this. Neither A or C satisfies this for all positive integers A, B, and C. Okay. Okay, so erase this. And the reason why I'm going to drop a link for reading GCD and Lcm in the description, because A and B, B and D rather, option B and D are from distributive properties of LCM and GCD. Okay, so let's go into proving option E. Okay, so now we have that the GCD of A and B divides B. Okay, and the GCD of A and B, so this is just by definition, divides A. Okay, so now we apply property 2. This implies that the GCD of A and B divides the okay, before I apply property 2, so let's look at this. So now we have that B, so B divides the LCM of B and C, and A divides the LCM of A and D. I mean, least common multiple. So the LCM of A and D is a multiple of A, so A has to divide. Okay, so now what does this imply? So we apply transitive rule of division. So we connect these two, we connect these two. So how that the GCD of A and B divides the LCM of B and C, and the GCD of A and B divides the LCM of D and A. Okay, so now we can apply the same thing for C and D. So I'll just do that here without talking much. So CD divides C, which divides and C, the GCD of C and D divides D, which divides the LCM of D and A. So I have that CD divides BC and CD divides DA. Okay, so we apply our first property. So look at it here. So if R divides A and R divides B, then it implies that R divides the GCD. Okay, so it's one of the things I said you can try and prove. So we connect these two, and we also connect these two. So what do we have? So let's scroll down a bit. We have the GCD of A and B divides the GCD of the LCM of B and C, and the LCM of D and A. And so we combine these two also. We have that the GCD of C and D divides the LCM of, sorry, the GCD of the LCM of B and C, and D and A. Okay, then look at our property 2. We have that if two numbers divide, so if R divides A and S divides A, then it means that LCM divides A. Okay, so we apply that here. So it means the LCM here on the dividing axis divides the GCD of the LCM of B and C and the LCM of D and A. Okay, and so that is option E. So we've shown that option E holds. Okay, so we can mark option E to be correct. So now I'll just give a quick proof for option option B and D. And to do that, so let me just quickly erase this. Okay. And to do that, so to prove for option B and D, I'm just going to define a function, okay? So we know that every number has unique factorization among its prime factors, okay? So I'm just going to define a function, and I'll leave it to you guys to prove the property of the function I'm going to state here. I won't prove the properties in this video, so as not to make this video very long, but you can always try and prove the property. I mean, it's fun trying problems on your own, okay? So let's say n is equal to alpha 1, p1 to the alpha 1, p2 to the alpha 2, and up to pk to the alpha k, okay? So now I define a set, kind of like a function, but yeah, a set. So relative to the integer d, to be the set of all prime powers that divide n. So basically, we have p1, p2, or just p1 to the 1 to the second power, so p1 squared up to p1 to the alpha 1, and then we have p2, and we have p2 squared, so on and so forth, okay? So basically, d of n is a set of p subscript I to the let me see, j, or let me see, to the t power, such that I ranges from 1 to k, and t ranges from 1 to alpha I. Okay, so basically this is what the set is, okay? And since every number has its own unique prime factorization, it means d of n is equal to d of m if and only if n is equal to m, okay? And then we have that the d of the GCD of n and m is equal to d of n intersect d of m. So you can try and prove this on your own. I won't prove it in this video. And we have d of the LCM of n and m is equal to d of n union d of m, okay? So now we look at B, and we okay, so we take d of both sides. So let me scroll down a bit. So if we can take d of both sides and we get same set, it means that the both of them are equal based on this property here, okay? So for option B, so d of the left hand side is same as d of A union, so d of the GCD of B and C is d of B intersect d of C, okay? And this is equal to, so let's just leave it. So for option B, so for B, this is the left hand side. After I simplified, I just keep the steps, so you can try and get this on your own. But there are properties of LCM, distributive properties of LCM and GCD, but I'm just trying to prove them for you guys, okay? And the right hand side Okay, so I'm not really going to an in-depth proof because I don't want this video to be very long. So the right hand side is, so the GCD of this, so we have D of A, so for the LCM of A and B, D of A union D of B. I'm looking for the GCD, so intersect D of A union D of C. Okay, so I want to show that these two sets are the same. So I'll just use a Venn diagram to show this quickly. And basically, for those of us that are conversant with logic, oh, sorry about that. It's misbehaving. I have no idea why. Okay. And so for those of us that are conversant with logarithm, with with logic, we'll see that these two sets, we can quickly show that these two sets are the same. So let me just quickly use Venn diagram to show this. So just draw 3 sets. Okay, and okay, so let this be D of A, D of B, and D of C. Okay, so the intersection of D of B and D of C, that's going to be this guy here. So I'm looking for that union with D of A. So I'll just color D of A with a different color. Let's say purple. Okay, so now I'll use a different insignia. So the union looks something like this. So I'll just draw it here. Okay, and so let's do for the right hand side. Okay. Erase this quickly. Okay. So for D of A union D of B, so D of A union D of B, so I'll just color it purple and with smaller circles. So D of A union D of B. And then I'll use a different color. Okay. Now D of A union D of C. So just shade that. So we're looking for the union. Okay, so the union is this same guy here, where we have both strokes and circles. So it's still something like this. Okay, so we see that the two sets are equivalent. Okay, so let's show for option C. So let me just mark for option. So for option B, we've shown that using, though not rigorous, but I'd like you guys to do the rigorous aspects on your own. Okay. Okay. So for option B, we have it. So for option C, for option D rather, D of so we have for option D. So we have D. So since we're talking of LCM, so let's just go. So we have D of the GCD. So D of the GCD of A and B union D of the GCD of A and C equals to D of A, so intersect because it's GCD, so D of A intersects D of the LCM of B and C. So I can just quickly do that. Okay, so this is the right hand side, and the left hand side. So we can simplify the left hand side further. So this is D of A intersect D of B union D of A intersect D of C. Okay, so this is the left hand side. Okay, so I'll just try and use logic to show this quickly. So we're looking for elements in both A and B, or elements in both A and C. Okay, so it means we're looking for elements in A that are also in B or also in C. So same thing as. So intersection is actually distributive over union, and vice versa. So this is another way we could have shown option B, but instead of drawing the Venn diagram, I'll just show it directly here. So looking for D of B union D of C. Okay, and we see that this is equal to the right hand side, and so we have it. So you can try and get a more rigorous proof on your own, but I don't want this video to be longer than this. So that'll be all for today, and we see that this question was actually faulty. So there are 3 options that satisfy for all positive integers. Okay, so that'll be all for this video, and I would link the for more in-depth reading on GCD and Lcm. I'll drop a link in the description. So don't forget to like, share, comment, and subscribe, and see you guys in the next video. Yeah, till then, goodbye guys.